this lesson. No more trig this unit. All right, yeah. All right, so what's that?
That makes me very happy.
I know it does. I know. I think you're not the only one. Trust me. All right, so here we go. We're into electric fields now. Electric fields are really a lot like gravitational fields, and it's hard for me to relate them to or show you the relationship because the problem with gravitational fields is in grade 11 physics we just hammer away that G is always 9.8. G is always 9.8. It's not really true though. As we looked earlier in this unit, is that G changes as the distance between us and Earth changes. The thing is in grade 11, we always look at when we're very, very close to Earth. And so we always say G is 9.8. But in fact, the gravitational field does change based on how far away you are from Earth. The same thing happens with an electric field. So when we have two objects close or with charged, an electric field is created, or just one thing, I should say. One electric charge creates an electric field. Now that electric field that is around it changes based on how far away you are from it. Just like the Earth has a gravitational field, and it changes dependent on how far away you are from Earth. Now, the electric field is what we call the electric field intensity. And it's this weird looking little E letter. It's a Greek letter that is epsilon, I believe. And so the electric field intensity, just like gravitational field strength, same idea, at any point is defined as the electric force per unit of charge. All right, so here is the formula. Well, all right, so we're going to look at two charges here. All right, so I'm looking at this situation. Let me get my pen here. All right, and we have some charge out here. And I'm going to say it is a positive charge. And we have some other charge here. I'm going to call it Q1, and I'm going to say this one is Q2. Now, because we have two charges, and this is the part that gets a little tricky here, is I'm going to define, I'm going to explain why, because your textbook does not do this, which makes it really confusing to learn this from a textbook. Q1 is the one I'm going to say. It's all about perspective again. It's experiencing the force. Because just like a gravitational field, there's a force of gravity. And an electric field, you have an electric force. I could also call it Q little e. All right, Q, the charge that's experiencing the force. Now, there's another force that I just wrote in there, Q2. Q2. I'm going to say that is the force, or that is the charge that is supplying the force. All right, so I'll call that QS. Pseudonames, I guess you could say. They have two names. Now, the electric field intensity talks about the amount of force per unit of charge. And so the formula that we have, because of that definition, we have epsilon, again, that is our electric field intensity, is equal to the amount of force per charge. And that charge that I've said is experiencing the force is Q1 right here, all right? Now, I could rearrange this formula, all right, and so that this formula could be Fe is equal to epsilon, our electric field intensity, times Q1. Now, this formula, and this is important because your textbook, again, does not talk about this whatsoever. And again, I'm going to explain how it can confuse you. And this is a formula for the electric force experienced by a charge Q1. So that's what that formula represents there. Now, again, I'm going to go back here to my diagram that I got here. Q2 is supplying the force. Now, when your electric field lines, I'm going to go back down here a little bit. Sorry if I'm jumping around. This is a lot of theory going on here, a lot of things that need to be explained. Now, when we have electric field lines, these are two positive charges here, both positive. And in terms of your electric field lines, field lines are directed outwards. Positive is always directed out. And so in this case, you can see the electric field lines are directed out, but because these are two positive charges, like charges, they repel each other. And so you can see the field lines almost run into each other. Now, the other situation that I have over on the right is I have a positive and negative. But again, the positive field lines are from a positive charge are directed outwards, and the negatives are directed inwards. All right, so that's important. And again, here you can see the attraction where the field lines from the positive charge are going outwards, but from the negative, they're going inwards. Because here's what can happen in this situation is in my electric field lines, which I'm going to draw in red, they are going outwards because Q2 here is supplying the force, which is supplied by the electric field lines. They're going outwards. Now, because this Q2 is supplying the force or the electric field lines, our electric field lines, in terms of directed towards Q1, are towards the left in this case. Now, because these two charges are positive and Q2 is repelling Q1, our force is also directed to the left. All right, so and our force is also going to the left. So they're both going to the left. The electric field lines have to be going to the left for Q2. And again, that's directed towards Q1. But because these charges repel each other, the force is also going to the left. Now, let's change it up here. I'm going over here to the right. I have a negative charge here. Here's my negative charge. And again, I'm going to draw in a Q2. There's my Q2. All right. Now, here's how things change up. My electric field lines, well, that doesn't change. It goes out from Q2. So epsilon goes this way. In fact, it goes in all different directions. It goes out from Q2. But in terms of how these two charges relate to each other, epsilon, the field lines are going outwards. And again, I'm going to call this Q1. But guess what, though? Things change a little bit here. Q1 here is negative. Q2 is positive. So the force experienced by Q1 is in the opposite direction because they are attracted. Opposites attract. So this time, the electric force that Q1 is going to experience goes to the right. All right, so there is a difference there. That's a huge difference between gravitational field strength and electric field intensity, which is you could call it electric field strength, is that with gravitational field strength, there's always an attraction. But with electric field strength, it can be an attraction or a repulsion. So there's two different things going on, and that's really what can confuse people. All right, so again, we're going to go over this a lot more, but it is a tough concept. Now, I'm also going to take this formula. All right, so I've already created one formula here. Fe is equal to epsilon times Q1. Now, what I could also do is that we looked at our electric force here in terms of Coulomb's law, which is K, so I'm just replacing Fe here, is Q1 times Q2, all right, divided by R squared, which again is the distance between these two charges. Now, I can't forget, I got this Q1 in the bottom. So to substitute that, I'm just going to do this. I'm going to go times 1 over Q1. So again, that's just to represent this Q1. Fe is represented by Q or K times Q1 times Q2 divided by R squared. Now, here's what I'm going to do. I got a Q1 in the top and a Q1 in the bottom. I'm going to divide those two out. All right. And so now I have a new formula. And this is what your textbook does not do. It makes it really confusing. Where my electric field strength is K, which is still that 8.99 times 10 to the power of 9, times Q2 divided by R squared. Now, what this formula represents is, this is the electric field supplied by charge Q2. All right, so I have one formula here talks about the electric force experienced by charge Q1, and this one talks about the electric field supplied by charge Q2. Now, why I'm pointing that out is your textbook, it just has Q's. It doesn't say Q2 and Q1, it says just Q. So you have no idea. It switches perspective. Very important. So I really want to stress that, all right? So one of these formulas talks about the charge supplying the force or supplying the field. The other formula talks about the electric force experienced by a charge. All right, so now we got that down. Hopefully, let's see what we can do. And if we don't have it down, well, we're going to check it out. All right, so here we go. Example 1. We have a test charge of Q1. So now you got to remember, hold on with these formulas. It's more about, it's not Q1, Q2. It's whether the force or the charge is experiencing the force or supplying the field. All right, so let's get that. Here we go. So a test charge of charge 2 times 10 to the power of negative 9 coulombs is placed in an electric field and experiences a force of 4.0 times 10 to the negative 9 newtons west. What is the electric field intensity at the location of the positive test charge? All right, so this charge here is experiencing, all right, this force. So when I look at it, I've got my charges, Q, and my charge here is 2 times 10, all right, to the power of negative 9 coulombs. The force, I've got, let's see here, our Fe equals 4 times 10 to the power of negative 9 newtons west. All right, and what we want to know is, at this point, what is the electric field intensity? Now, again, I want to relate this to gravitational field strength. This would be like saying, this is how much you weigh, all right? Find the gravitational field strength at this height. It's kind of what it's saying, all right? In a weird way, again, trying to relate it. So when we are looking at our formulas, I'm going to use Fe, because we're talking about an electric force being experienced. So I'm going to use Fe is equal to epsilon times, in my formula it says Q1, but I'm going to put QE. That's the charge that's being experiencing the force. All right, so now I'm going to plug in my information. And after this, I'm going to explain a little bit more what's happening. What's the situation? All right, so my Fe is 4 times 10 to the power of negative 9. Find my buttons here. Epsilon. Ooh, what am I going to use there for that symbol? Let's go with an E, I guess. Epsilon, and my charge is 2 times 10 to the power of negative 9. All right, so here's what I'm going to do. I want to get epsilon by itself. Whoa, I missed something here. I missed direction. Can't do that. I don't want to lose marks. Here we go, west. All right, so I'm going to divide both sides because I want to get epsilon here by itself. So I'm going to divide both sides by 2 times 10 to the power of negative 9. All right, so we do that. 2 times 10 to the power of negative 9. Gone. All right. All right, so now I'm going to find my epsilon. So I'm going to divide these two. Well, the times 10 to the negative 9s are going to cancel out, actually. That's easy enough. 4 divided by 2. All right, and so I'm gonna 4 divided by 2 is just 2. Now, what are the units for epsilon? That's something I didn't go through earlier. It is field intensity, newtons per coulomb, because it's the amount of force per charge. And in this case, the direction is west. Okay, so that is my answer. What the heck does that mean? Kind of important, right? All right, so here's what we have. We have our charge. So I'm just going to draw a little diagram here. Here's my Q1 charge. There's Q1 right here, the charge I'm talking about. It's plus. It is experiencing a force that's going this way. All right, the force is going west. That's the important part here. My electric field intensity, because it's going west, let's get that, it's being pushed left, right? So that means if it's being repelled left. If it's being pushed left, it's being repelled. So my random charge over here somewhere is a positive charge, which means the electric field lines also must be heading west. All right, so that is what we're looking at. So there's some positive charge out here that has an electric field lines pointing west. And because our Q1 here is a positive charge, the force is pushing it west. Now, I'm going to check out a different situation. Well, predict the force that result on a test charge Q1 if Q1 was replaced by Q2. So now I'm pretending there's a different charge here, but yet the same positive charge out here. All right, so here's what we got. We know that epsilon, which is created by this random positive charge I've talked about, is 2 newtons per coulomb, coulomb west. We have this new charge that I'm calling Q2. But again, it is the charge that is experiencing the force. All right, now it is -9 times 10 to the -6 coulombs. What I want to know is what force is this experiencing? Now again, when I'm relating this question to gravitational field strength is, say we're on the planet, well, which we are, we all experience on ground level a g-force of 9.8 meters per second squared. But we all have a different force of gravity based on our mass. Well, this charge is going to experience a different force because it is a different charge, even though it's in the same electric field strength. All right, so now again, I'm going to use my formula here. Fe is equal to epsilon times QE, again, that because it's the charge experiencing the force. All right, so here we go. Do a little little substituting in. So I got Fe is equal to. Now, what am I going to rock with here? I'm going to say that west is negative, east is positive. Okay, so when I put in for epsilon here, I'm going to put in a -2 because it's west. All right, now my charge here is I'm just looking at the charge. I'm going to put in my -9, all right, times 10, what is it, to the power of -6. I'm going to show you what happens here, and then I'm going to explain what's going on. All right, so now I multiply those two. All right, so I have a negative times a negative, so it's going to be a positive answer here. And let's see here. Whoops, I gotta grab my calculator. All right, so multiply those two numbers, and I get 1.8 times 10 to the power of -5. Now, it's positive. All right. Now, to make this a vector, because it's positive, and it's newtons, by the way, I better not forget my units here. And I already said west is negative, right? So that means this force that this charge is experienced goes east. So let me draw that up here. I'm going to leave this picture up here I got going on. So again, I got this same charge up here, some random positive charge. It has an electric field, epsilon, that we already said is, that I already figured is 2 newtons per coulomb west, all right? But the charge we're talking about now is Q2. It is negative. Look at Q1 up here. It's positive, right? We switched up charges. This one's negative. And so because of this, some random positive charge up here, and I only know that because of my electric field strength is going to the west, so that means the positive charge had to be over here. These are opposite charges. And so that means this time there's an attraction. And so my force, electric force, is now going east. And that again is the huge difference between gravitational field strength, which can only have attraction, and electric field intensity, which can both have attraction in this case, or up here in our first part A, repulsion. All right, so hopefully I explained that pretty good. Again, tough concept. Now, get to the other formula. Here we go. We have a situation here. We got our 2 charges, Q1, Q2, are located 80 centimeters apart. That's an issue. Okay, so that's, I got to convert that to our standard units. Now, a positive test charge is located at point P. Bingo. All right, there it is, which is 55 centimeters from Q1. All right, along a line connecting the 2. All right, so let's get some distances here. So, all right, what are we looking for? Sorry. A, what is the electric field intensity at the location? All right, so we don't know what charge is here, but what we want to do is figure out what epsilon, what electric field strength are we going to feel here? We don't know what the charge is yet because it doesn't matter. It's what are we going to feel here? So it's just kind of like saying, what is our gravitational field strength at an altitude of 400 kilometers above the Earth's surface? Doesn't matter what object is there. We just want to know what the gravitational field strength is. And that's what we're looking at here. Now, again, I want to get my distances right here. So let's see. These 2 are 80 centimeters apart. Okay. A positive test charge is located at point P, which is 55 centimeters from Q1. All right. So we got 0.55 meters over here. And since they're 80 centimeters apart, do some math. It's going to be 0.25 meters or 25 centimeters in here. All right, so now this is where your textbook is terrible, terrible. What we want to do is look at the electric field strength, field intensity at point P. Well, what we're going to do is see, first of all, what field strength is created by charge 1. And I have a formula for that, which is K times, and again, I'm going to use QS because Q is supplying the force, only this time it is charge 1 that's supplying the force, divided by, D squared or R squared. Either way, it's the distance or the radius between the 2 points. All right, so now I'm going to figure out what field strength that charge is supplying 55 centimeters away, or 0.55 meters. All right, so I'm going to substitute it in my formula here. So again, K is 8.99 times, got an X here. I guess it could be X times 10 to the power of 9. All right, the charge, what's the charge on our first charge here? 5 times 10 to the power of -7. All right, and of course that is divided by our distance squared. So let's see here, throw that down here. And again, the distance is 0.55 and squared. All right, now the gravitational field strength, let's check it out, is, let's see, I'm going to do some multiplying here and then divide by 0.55 squared. And here's what I'm getting. So I pipe that into my calculator, and I'm getting it's 14859.5. And again, the units are newtons per coulomb. Now I need a direction here, right? It's a positive charge. Because it's positive, our electric field lines go outwards. So when I'm talking about P, the electric field lines, let me actually draw them in here a little bit in green. In terms of P, it's going to push this way or out this way or out. Everything's outwards. But because we're looking at Q, that means this electric field line is going to be directed to the right, because again, it is a positive charge. So that is what P, at point P, this electric field strength would be because of charge 1. But we got 2 charges here. So now what I'm going to do is look at the electric field created by charge 2 here, which is negative, by the way. But again, I'm going to use the formula. Epsilon is equal to K times Q2, or Q2, which in this case is still supplying an electric field, divided by R squared. All right, so this time, our second electric field, and I'm going to pump in my numbers. So let's see here. We have 8.99 times 10 to the power of 9. There's our constant. This is charge. What's the charge on Q2? Negative 4 times 10 to the power of 8. Again, it doesn't matter about the sign, because we have to figure out the direction. So the sign doesn't tell us anything. It's the magnitude we're interested in. Negative 8 there. All right. And again, I have to divide it by our distance squared, which is 25 centimeters. So, or 0.25 meters. And again, we have to square it. All right. Now, epsilon 2. I should put a little vector symbol in there because we have direction. Now, I got to do a little bit of math here again, which I've gone over with scientific notation. I know that some of you still struggle with it. And I'm getting 5,753.6. Again, it's how much force per bit of charge. Just like a gravitational field strength is how much force per kilogram. All right, and now direction. Check this out. It is negative. So if this charge is negative, all the field lines go the opposite direction. So in terms of point P, it's going to pull in this way, pull in this way, pull in this way. But again, in terms of our point P, our reference point here, it's going to pull it to the right as well. And so if we are trying to find the net electric field, these forces are actually working together. They're both going to the right. And so I'm going to add these two together. So even though one charge is positive, one's negative, because they're on the opposite side of P, they are working together. And so if I take my 14,859.5, whoops, 0.5, and I add my 5,753.6, it equals, again, I'm adding them together, I get 20,613.1 newtons per coulomb. And, well, they're both going right, so to the right. There we go. All right. So that's figuring out our field. Now, a new charge of Q3. We're actually going to put a point into point P. Determine the electric force on this new charge. All right, so here's what we do know. We know the electric field strength at that point. And, well, I'm just going to, I wonder if I can copy this. Don't know how to do that yet, I guess. See. All right. Trying to get fancy with my new computer. Let's just go back to the original. All right. So again, my electric field strength here is 20,613.1 newtons per coulomb, and it's to the right. Oops, to the right. Okay, so we pop in a charge there. The charge that we are looking at, now this charge is experiencing this force, so I'm going to call it QE. All right, is equal to 2 times 10 to the power of -9 coulombs. And what we're looking at is the electric force that it experiences. So again, this is where I'm using my formula of Fe is equal to epsilon times the charge that is experiencing the force that's in the field. All right, so Fe, now again, I'm going to make right positive. And so let's see here what we get. Plug in. And so I've got my 20,000, positive 20,000, because we're going to the right here. 613.1. Don't forget the 0.1. Again, it's positive because we have it's going to the right. Times 10 to the power of -9. All right, and when I here multiply those together, my electric force is equal to, let's see, I multiply those two together, I get 4.12 times 10 to the power of -5, and it's a force, newtons, and because it's positive, this force is to the right. Okay, so what does that mean, right? Let's make sense of that. Look at this charge, positive charge right here. So what happened in our original situation? Hold on here, I'm going to try to get fancy again. I can't find the erase button. That's, oh, there it is. Let's get rid of this. All right, so here's what we did. We pretended I popped a big positive charge here, right? Well, look what's happening. It's saying the force is pushing us to the right. That's what our answer is saying. Well, this charge is positive, so they're repelling. So that force is going to go this way. All right, this charge here is negative. It's going to attract, so our force is also going to the right. And so that is why our force on this charge P would in the end be pushing it to the right. All right, so again, conceptually, tough lesson,